Hello everyone, I'm Shixiong Zhao. I will present HAMS, a machine learning serving system that provides fast and efficient fault tolerance for machine learning service graph. This work is a cooperation between HKU, USTC, and Huawei. My supervisor is Dr. He Mingcui. These days, machine learning models are prevalently deployed in mission-critical services. Here is a perception modular from my autopilot software framework. In this graph, machine learning models are deployed on different computing units. When a car is running, this service graph takes data collected from sensors and generates the perception information. In such a graph, a machine learning model can be stateless or stateful. A model is stateful when it holds an internal state or is continuously fine-tuned by new training data. In such a machine learning service graph, if a stateful model fails, it's crucial to efficiently recover the model while keeping a low normal case performance overhead. Moreover, in a machine learning model, the output of the model is very sensitive to the internal parameters. Even a slightly inconsistency of the parameters after failover may cause a different inference result. For example, in our evaluation, we recovered a stateful object detection service using a record replay approach. Before failover, it outputs the track as the highest ranking, but after failover, it outputs the cloud as the highest ranking. This inconsistent ranking during failover is because of the GPU non-determinisms. Specifically, in GPU multithreading, GPUs need to randomly schedule the addition of tensors, but the addition of rounded floating point is not associative. Therefore, even given the same input sequence of training data, the replayed model can often give a different predicted ranking result. Hence, traditional record replay fault tolerance systems like lineage stash often assume no non-determinism exists in computation. We give an example to illustrate how record replay systems fail to handle non-determinism. In this graph, the RCN model for object detection takes two input streams, one for serving and one for training. The training input will continuously update the model state. We record the model state for every 100 inputs. When a failure occurs, we boot up a new computing unit and copy the record. After that, we replay the same sequence of inputs to recover the state. But since the computation of GPU is non-deterministic, the model is recovered to a slightly different state. When the model outputs the prediction, the results are dramatically different for the downstream modulus. Before failure, it predicts the track, and after failure, it tells the cloud. We did an experiment to show how often GPU's non-determinism can cause such inconsistency. We replay the training process for a masked RCN model from a different checkpoint interval. The results show that longer replay interval causes higher occurrence of 8-bit loss inconsistency and leads to a classification error on the test set. Since record replay approach fails, primary backup approach like RAMUS is effective to handle non-determinism. We give an example to show how RAMUS works. For each stateful model, a backup hot standby. When the request 101 arrives, model 1's state is changed. Then the state 101 is held by the model 1's primary and we copy the state 101 to the host buffer. Before the state copy finishes, the primary should completely stop because any computation may change the state. This is the first source that makes RAMUS throughput low. Primary must stop to wait for state copy, and such a long idle time will cause a low hardware utilization. After the state copy, model 1's primary is allowed to process request 102, but the request 101 is still held to wait for the transfers of state 101 to finish. When the state transfer finishes, the request 101 can go to the next model. The request will be held again for another state copy and another state transfer, and after that, the request can go to the downstreams. Here comes the source 2 that makes RAMUS slow. Through a computation, a request should be held by RAMUS multiple times, hence the latency overhead will be dramatic. Our experiment shows that RAMUS has a large overhead coming from a total holding time of 140 milliseconds, including waiting for the state copy and waiting for the state transfer. To make a primary backup system efficient, we have three observations for HAMS. First, in machine learning stateful operators, Only a small portion of dirty memory is the operator's real state. While RAMS replicates all dirty memories, we design HAMS as a white box system that replicates only the useful state, which only contains the model's parameter or memory cells. Second, stateful machine learning operators often follow a compute then update manner. In HAMS, we allow the latter request's compute stage to overlap with the former request state copy, and hence the primary do not need to stop and idle. Third, to eliminate the holding delay, HAMS directly release requests to downstreams inside the graph without holding. We maintain the correctness of fault tolerance by designing a non-stop primary backup protocol based on these two key observations. We will show how basic protocol of HAMS works. Here is the same service graph as the previous object detection example. When request 101 is processed by model 1's primary, the request output is directly released to the downstream model 2, and simultaneously we start transfer state 101 to the backup. Meanwhile, since requests are not following a compute then update manner, the compute stage of request 102 can directly start because it will not modify the state. Then the request 101 goes to model 2, and the model 2 state 101 is also transferred to the backup. Note that at this point, the request 101 is not allowed to leave the graph, and when all states are transferred to the backups, the request 101 is allowed to leave the graph. Overall, there are mainly two reasons that makes HAMS much more efficient than RAMS. First, when the local copy of state 101 is happening, the computation of request 102 is already started. Hence, the throughput overhead of HAMS is small. Second, in HAMS, there are almost no requests holding on the computation critical path, and hence the latency overhead is small. In our evaluation, HAMS has only 28 millisecond latency overhead. However, the full implementation protocol of HAMS is much more subtle than just the basic ideas in the last slide. Our protocol guarantees the consistency when the requests are fast released without holding. HAMS has a library for developers to easily identify the compute then update boundary, and we provide structural language for developers to specify a service graph. For more implementation details, please read our paper. We compared HAMS with a bare metal system, a record replay system lineage stash, and HAMS RAMS. To make the evaluation fair, HAMS RAMS replicates only a stateful model's parameter or memory cells, and is actually faster than the black box RAMS. Here are the evaluation setups. And here is the application composition graph. Our evaluation mainly focuses on two questions. How is the normal case overhead of HAMS compared to relevant systems? And how is the recovery time of HAMS compared to the relevant systems? Overall, HAMS achieved a low latency overhead which is comparable to lineage stash, while HAMS RAMS had a latency overhead that is up to 97%. Also, the throughput overhead of HAMS is low, and the throughput overhead of HAMS RAMS is very high. Importantly, HAMS captures GPU non-determinism, but the lineage stash is not designed to do so. HAMS takes only sub-second recovery time to recover stateful model, which is much faster than lineage stash. LS takes tens to hundreds of seconds to recover stateful model because LS need to replay a long sequence of input in order to keep the normal case overhead low. If LS takes a short checkpoint interval for fast recovery, the normal case overhead will be prohibitive. In conclusion, HAMS is the first system that handles non-determinism in machine learning service graph efficiently. HAMS can serve as a fault tolerance component in many machine learning serving systems like Clipper and TensorFlow serving. In near future, we plan to provide an efficient state migration in edge computing, and we will extend our open source project to TensorFlow and MSNet. Thanks for your listening, and you are welcome to ask questions.